Okay, hello everyone, and welcome to our YEA Big Physics problem lecture. So the problem for this week is from Yusufo, and this infinitely long wire has a linear charge density of negative lambda along the z-axis, and there's also an infinitely long insulating cylindrical shell around it, and yeah, basically the system is immersed in an external magnetic field B0 in the z direction, and the system is initially at rest, and then at starting at t equals 0, the magnetic field is slowly reduced to 0 over a long time t that is large, and we want to find an expression for the final angular velocity omega. Okay, so first we can try and find the induced electric field inside the cylinder. So to do this, we use Faraday's law. We can write integral E dot dl is equal to negative d, and this is the magnetic flux over dt. Okay, so it's integral E over dl. The magnetic field is pointing up in the z direction. So then we can see that from the right hand rule, if you put your thumb in the z vertical direction, then your fingers curl around in the circle in the counterclockwise direction. So then you can see that the induced electric field is going this way. So then if we take this dot dl, since it curls around this cylinder once, then when we integrate it, it's just going to be E times the distance, which is just the circumference of the circle, and the radius of this circle is a, so it's just 2 pi a. And this is equal to negative d of the magnetic flux over dt, and the magnetic flux we know is equal to it's equal to negative dB over dt, which is the rate of change of the magnetic field, and multiplied by the area that this magnetic field goes through for the shell, and that's just going to be this area since it goes through like that, and that is pi a squared. So then we get that E, the electric field, is just equal to this cancels. It's just equal to negative a over 2 times dB over dt. Okay. So now this induced electric field, since there's an electric field now, that means since the surface of the shell is charged, there's going to be a force, and this force is going to give the cylinder a torque, which makes it spin. And so basically the force we know is E times Q, which is the charge. And so if we look at, say, this small like section here, yeah, we can see that it should be the torque is equal to it's equal to E times the charge is the surface charge density. It tells us is lambda over 2 pi a, and this is only for this small section, but the force we know is going to act is going to like basically, I guess, work across this this entire circumference. So we need to multiply this by the length of the circumference, which is 2 pi a. And so this is the force on it, so that we just need to multiply again by the radius a to find the torque. And we know that torque is just equal to I alpha, and this is I d omega over dt. Okay, so now we just get that this is, well, we can cancel this out. It's equal to E times lambda alpha, which is negative a lambda a squared over 2 dB over dt, which is equal to I times d omega over dt. Okay, so now, yeah, so we want d omega over dt, of course. So d omega over dt is equal to negative lambda a squared over 2I dB over dt. Okay, so now we just have to integrate over t. And so we integrate both sides and we get that omega should be equal to negative, this first part is constant, so negative lambda a squared over 2I. And when we integrate dB over dt, we just get bt of minus b0. And this is because, yeah, when we integrate, it's just b, and when we're integrating from the time 0 to time t, so it's just the final b minus the original b. Okay, so in the problem, it tells us that the magnetic field B decreases to 0, but at the end, after a time big T, the magnetic field actually is at 0 because this cylinder is now rotating, and so when there's like a moving current, this generates a magnetic field. So then, to find this new magnetic, well, this induced magnetic field, we just use Ampere's law, which tells us that this integral B, let's say B prime, which is induced field, magnetic field, dot dl is equal to mu 0 I, and mu 0, well, we already have I for the moment inertia, so let's call this mu 0 I, I don't know, 0 or something, which is the enclosed current. Okay, so then we know that I0 is equal to the current, which is the charge over the time. So to find this, we basically look at this circle. So all the charge on here is going to pass, it's going to go in circles around here. So then the total, so let's say in the time t, the time t is the period it takes for the, I guess, the charge to circle around. Then all of the charge on the circle will move around. So that charge is going to be equal to that charge is just going to be Q, which is so that's just the lambda, the charge density, or lambda over 2 pi a, I believe. Yeah, lambda over 2 pi a, and or wait a second, times. Oh, okay, never mind. Yeah, so here, so basically the amount of charge that circles around here is just going to be lambda. Since the surface charge density is lambda over 2 pi a, but we still need to multiply by another 2 pi a to find the total charge on this circle. So all of this charge, which is these 2 pi a's cancel, so we just get lambda. So all the total charge like here, lambda, just moves around in the circle in the time it takes for it to like in that time. So the amount of time it takes is just going to be oh it's just going to be 2 pi over omega. And because it rotates at omega and it's just the period it takes to circle around will rotate at omega, that's just 2 pi over omega. So it's lambda over 2 pi over omega. So that is lambda omega over 2 pi here. So that's the enclosed, so that's I, 0. So now we go look back at this integral, and yeah, we just integrate this and we get that this bt is equal to, let's see, we integrate mu 0 times yeah, times 4. Well, let me think just a sec. Yeah, okay, so we get that this is equal to, wait, this part is equal to mu 0 I0 is lambda omega mu 0 over 2 pi. So then yeah, well, we integrate this, we just get that the bt should be equal to mu 0 is equal to, oh yeah, okay. So bt is times, since when we integrate over dl, it's going to be multiplied just by the circumference, because b goes around here and we're just integrating over this circle, circumference 2 pi a, so bt times 2 pi a is equal to lambda omega mu 0 over 2 pi. So bt is equal to lambda omega mu 0 over 4 pi squared a. I believe, yeah. Okay, so now we look back here. We can just plug in bt now. So we get omega is equal to, let's see, okay, this is gonna be, okay, negative lambda a squared over 2I times bt minus b0, so that's lambda omega mu 0 over 4 pi squared a minus b0, and this is equal to negative lambda squared negative lambda squared a omega mu 0 over 8, yeah, 8I pi squared, yeah, pi squared minus, or in this case it becomes plus lambda a squared b0 over 2I. Okay, so now we can move omega to the other side. We get omega times 8I pi squared plus lambda squared a mu 0 over 8I pi squared is equal to lambda a squared b0 over 2I. So then omega is just equal to, okay, all right, let's just make this, yeah, just make this 1 actually plus here, which is probably easier. So then we just get lambda a squared b0 over 2I over 1 plus lambda squared a mu 0 over ai I squared. And this is, yeah, this is the correct. Yeah, this is, so that's the answer. Yeah. All right, so that's it. This is the answer, final answer, which is a bit complicated, but yeah. So yeah, that was a tough problem, but hopefully you learned something. So that's it for this week then. So thank you for listening. Bye.